In this lecture we talk about regular functions. So you start with an algebraic set X, and from here you construct this ring K of X. So you know how to construct this ring. You first fix your base ring, or the space in which you want to embed this X. So say this ring is this K y1, y2, y3 all the way to yn, and then you have the ideal corresponding to this algebraic set X. So your K of X is nothing but A over your ideal. So do not confuse this with this ring, this K of small x. So if it is confusing, you replace this capital X with V, because algebraic set is just V. So once you have this ring, then you can form a field of fractions of K of X. So field of fractions just looks like f by g, so rational functions where f is in K of X, so f is in this and g is also in this, so g is also belonging to this. So you pick a rational function from this field of fractions. So notice that this bracket is now round rather than square because it's a field of fractions. So rational function, say phi, which is equal to f by g. So it is regular at a point in the variety. So you pick a point on your algebraic set X if the denominator is not 0, and a function that is regular on the entire algebraic set X, that becomes an element of K of X. So you have a rational function on a point, but if you take this rational function on the entire set, it becomes a polynomial. So let us talk a bit more about this. So the story is this: you have your algebraic set X here, right here, and you form open sets. So to form open sets, first you choose a function. So say you have chosen a function g1 equals to 0. So corresponding to g1 equals to 0, you have this green line, and you form open set u of g1 by deleting these 2 points right here. So g1 is not equal to 0 on rest of the white set. So say a rational function here is f1 by g1, and you are working in this algebraic set X, so u of g1 lies within X. Now again you take X and cut a different open set. So say you have another function, say g of 2. This g of 2 is 0. So you remove these 2 points from your algebraic set X and you will get u of g2, where g2 will not be 0 on this u of g2. So g2 will not be 0. So these two sets, u of g1 and u of g2, they cover this algebraic set X. So X lies within this cover. And say functions of u of g2 are of the form f2 by g2, obviously because g2 is not 0. So what we want to do is we want to glue these two functions together. We want to glue these two functions together to get a function globally, that is a function which is on the entire algebraic set X. So if you have this entire algebraic set X, then it is closed, and this function has to come from K of X, because corresponding to this algebraic set X, you have this ring K of X. Obviously corresponding to this set, this ring becomes bigger. You have 1 by g1, you adjoin 1 by g1 to it. That's why you have function f1 by g1. Similarly here on ug2, the ring becomes bigger. It becomes, you adjoin 1 by g2 to it. So obviously it contains K of X, but it is just bigger ring. But when you get back on the algebraic set X, you just have K of X. So what we want to do is we want to glue these two functions, so you get a polynomial on K of X. So you get some phi here, which is just a polynomial. And the entire purpose here of this lecture is to show that you can glue these rational functions here and here to get a polynomial right here. So a function that is regular on the entire set X, this is an element of K of X. So we start with a regular function phi K of X. So you say you start with this function. Now on this open set, you write it as by fx by gx with this g of x is not 0. So on this open set, you just pick up a point here. So at this point, this g1 of x is not 0. So this g1 of this small x lies within this algebraic set X. So this rational function makes sense. The denominator is non-zero. So you keep taking all the points on this set X. So there are uncountably many points on this variety which we have drawn here. So we could have a finite number of points too, but the way we have drawn our variety, we have uncountably many points. So you take all those functions which do not vanish on each and every point. So you just have to worry about a single point here. So a function which does not vanish here might vanish at another point, say x2, but you are just worried about this point right now. So the denominator is not 0. So you take all such denominators, and all these denominators generate an ideal. Now this ideal would be finitely generated. Now this ideal is finitely generated because the ring which we have chosen here, this is Noetherian. And say it is generated by a finite number of these functions, gx1, gx2, all the way to gxn. Now this is exactly the same way we discussed quasi-compactness. So what you're trying to do is you're just trying to build a cover of your space X. So you can think it as building a cover of space X. So all these functions you have. So for example, if you have g1 is not 0, so you have a point x1. So then you take g of x1 not 0. This will define a set ugx1. So this open set forms part of the cover of X. So say all these ideals generate this ideal A. Now the vanishing set of A would be null set. Now this is simply because this g of x, this lies in this ideal, because obviously we have just taken a finitely many functions which would generate this function. So this g of x lies in here, but this g of x is not 0. So since this function which lies in this ideal does not vanish, so vanishing set of A is null set. So because this function is not vanishing on the algebraic set X. So on the algebraic set X, you have a function in the ideal which is non-zero. So therefore the vanishing set is just a null set. This function just does not vanish. So by Null-Celensarts, then this A generates 1. So remember, in Null-Celensarts you have this, if you have a proper ideal, then the vanishing set of the ideal is not a null set. So you are saying contrapositive. So if vanishing set of I is the null set, this would imply I is equal to A, and that is what it is. So this A generates 1 by Null-Celensarts. So hence there are functions v1, v2 all the way to vn such that all these functions are polynomials such that this sum is 1. So what you're taking is you're taking v1 multiplying with gx1. So you have v1 gx1 plus v2 gx2 all the way to vn gxn is 1. We are simply saying that these are generating 1 because I is equal to A. So this is it. Now you multiply both sides by this function phi. So you multiply this side by phi. Now when you multiply here, phi times v1 times gx1 plus phi times v2 times gx2 all the way to phi times vn times gxn, this is equal to phi. But now you have to think about it locally. So what is this phi on gx1? So phi on gx1, so globally it looks like this, but on this open set here, so on this open set here, it takes the form f1 by g1. So locally, so this phi locally looks like fx by gx. So this phi you can rewrite it as, so here you rewrite it as f of x1 by gx1. Here you write it as f of x2 by gx2 because you're taking its local value, so phi on this open set. And then here you have f of xn by gxn. Do the cancellation. So what you have left is just a polynomial. So this is from k of x and f of xi is from k of x. So you just have a polynomial. So this will make more sense once we talk about sheaves, when we will glue local sections to get a global section. So you can find all this material on page 36 of Shafarevich's book Basic Algebraic Geometry. So this you will find on page 36. This is second edition, and this is theorem 4.